Okay, welcome to this explainer. Today we are diving straight into the absolutely high-stakes, zero-margin-for-error engineering behind electric vehicle inverters. We're talking about the beating heart of the EV drivetrain here, and preventing these power modules from overheating is literally a matter of life and death for the vehicle's components. We're going to unpack the incredibly sophisticated defense systems used to manage thermal faults in IGBT and silicon carbide MOSFETs, making sure the power stage operates safely even under the most extreme, brutal conditions imaginable.
Now, to really grasp the stakes here, you have to ask yourself, what actually happens when millions of watts generate fatal heat in the blink of an eye? Just imagine an EV, out on the highway, pushing its dual-motor controller to the absolute limit. In mere fractions of a second, extreme electrical switching can cause those power chips to skyrocket in temperature. And if that heat isn't managed instantly, well, the physical materials inside the inverter will literally melt down. It's a catastrophic failure of the entire drive system waiting to happen.
So, here is the absolutely crucial takeaway. This isn't just about saving a microchip from burning out. Not at all. It's about hitting strict ASIL D safety goals, which is the highest, most rigorous classification of automotive safety out there. The number one priority? Preventing dangerous, unexpected vehicle acceleration or sudden braking. If an inverter fails, the motor can get unpredictable commands, and boom, you have unexpected torque. To defend against that, our reaction times can't be in seconds. We're talking milliseconds, sometimes even microseconds.
To break down this massive engineering feat, we're going to walk through 5 key pillars: root cause analysis, co-diagnostic architecture, DFMEA key design controls, PFMEA process controls, and finally, DVPNR production validation.
All right, let's kick things off with Pillar 1, the threat. This is our root cause failure analysis.
So, how does an inverter actually die? It's basically a rapid chain reaction. First up, extreme electrical stress from high-frequency switching builds up massive heat in the microscopic die. Then, as the module rapidly heats up and cools down, that thermal expansion and contraction literally squeezes the thermal paste right out. Engineers call this the pump-out effect or dry-out. Third, without that crucial cooling layer, the internal aluminum or copper wire bonds fatigue and literally lift off the chip. Finally, losing those pathways creates massive internal resistance, forming these fatal hotspots and ending in total thermal runaway. The whole shebang just melts down.
And if that chain reaction wasn't scary enough, get this number in your head, 1390. If the cooling degrades, or say a rotor position failure improperly forces the system into a high-speed active short circuit, the motor's demagnetization, back EMF, can generate a massive 1390 amp peak steady-state short circuit current. I mean, that much current instantly shatters the chip's safe operating area. It hammers the power module with a thermal shock it simply cannot absorb without an automated defense system stepping in.
Which brings us perfectly to Pillar 2, the shield. This is where we look at the hardware and software co-diagnostic architecture.
This is where things get really fascinating. There is a stark contrast between our physical and digital defenses here. You've got your physical NTC temperature sensor, right? But it has a thermal conduction lag of 50 to 200 milliseconds. Now, in the EV world, 200 milliseconds is practically a lifetime. It's way too slow to catch a sudden heat spike. So to solve this, engineers pair it with a software observer. This software runs a Cower or Foster RC thermal network model. Think of it like a highly advanced weather forecasting algorithm, but it acts as an instant, predictive digital twin of the chip's temperature, calculating in real time based on current and voltage loss.
But hey, software can't do it all alone. We have to think in microseconds. The analog hardware acts as a direct hardwired safety net. The main microcontroller is constantly checking that the physical NTC sensor voltage stays strictly between 0.5 and 4.5 volts, just to make sure the wire itself hasn't broken. At the exact same time, smart isolation gate drivers like the NXP GD3100 or the Infineon IC Driver ICE Driver are monitoring their own junction temperatures. If they detect a fatal error like desaturation, they don't even bother waiting to talk to the main computer. They autonomously shut down in less than 2 microseconds. 2 microseconds.
So, what happens when the system actually catches an error? It dynamically shifts its fallback strategy based on just how bad the problem is and how fast the car is moving. Say the inverter hits a light overtemp of 125 degrees. The system uses a smooth thermal derating, gently limiting the torque. No big deal. But if it hits a critical 175 degrees, the computer only has 60 milliseconds to react.
If you're flying down the highway over 80 kilometers an hour, it executes a stepwise active short circuit to clamp the voltage safely under 720 volts. If the car is moving slow, it triggers an active open circuit, safely freewheeling that current down to zero.
Moving right along to Pillar 3, the blueprint. These are the DFMEA key design controls, where we literally engineer the threat out of existence before the car is even built.
This all starts at the architectural level. By engineering custom integrated pin fins and microchannels directly onto the cooling block, we structurally guarantee massive heat dissipation, keeping that thermal resistance under 0.1 Kelvin per watt. Also, and this is a big one, during high-speed switching, sudden voltage spikes can actually accidentally turn a dormant transistor back on. To stop that fatal mistriggering, the blueprint mandates an active Miller clamp, pulling a negative 5-volt bias. It's essentially slopping a heavy electronic deadbolt on the transistor. Plus, we only use ultra-precise thin-film resistors and C0G ceramic capacitors so that intense heat doesn't warp our sensor readings.
Now check out this number, 960 degrees Celsius. That is the melting point of the nanosilver sintering we use to attach the die. We completely replace traditional solder paste with this stuff. Why? Because traditional solder cracks under severe thermal cycling. But nanosilver sintering? It gives us 3 to 5 times the thermal conductivity and easily survives those extreme power cycles. It is an absolute game changer for the lifespan of the module.
All right, the design is solid, but now we have to actually build it perfectly. Enter Pillar 4, the forge. Let's look at the PFMEA manufacturing process controls.
You know, human eyes just aren't going to cut it for this level of precision. On the assembly line, we mandate 100% automated acoustic scanning or 3D X-rays just to look inside the solid metal for microscopic defects. Hand-applying thermal paste? Completely banned. We use automated 3D laser profilers to ensure the paste is exactly 50 micrometers thick. Not 40, not 60, exactly 50. The ultrasonic wire bonders actually monitor their own physical deformation in real time, and we regularly do destructive pull tests on batches. To top it off, a 4-bar high-pressure helium leak test guarantees water will never, ever breach those high-voltage barriers.
And there is a hard zero-tolerance rule on the factory floor. The total voiding rate must be strictly less than 5%. Voiding basically means microscopic air bubbles trapped in that crucial silver sintering layer. If the automated X-ray sees a void larger than 5%, the machine automatically locks down. Actually, it has to, because a single microscopic air bubble in the wrong spot creates a localized hotspot that will completely destroy the chip. Zero tolerance for short.
Finally, we arrive at Pillar 5, the trial. This is the DVPNR production validation phase. This is the ultimate gauntlet these inverters have to survive before they ever see mass production. We subject them to over 100,000 extreme power cycles, intentionally shifting their junction temperatures by over 80 Kelvin over and over again. We shake them violently on 3-axis vibration tables while simultaneously freezing and baking them from -40 to 150 degrees Celsius. And finally, the grand finale. We strap them to a hardware-in-the-loop rig, spin them up to 12,000 RPMs under full load, and intentionally cut their cooling water just to prove the software catches it in time. And when we inject that fatal fault at 12,000 RPM, the system has to execute its fallback flawlessly. It absolutely must clamp the voltage spike under 720 volts. It has to contain the runaway short circuit current to 550 amps max. And crucially, this is the real magic trick. It has to do all of this while keeping the torque derating incredibly smooth. It cannot jolt the driver with more than 50 Newton meters of sudden braking force. Because think about it, causing a driver to lose control of the vehicle while you're trying to save a piece of hardware totally defeats the entire purpose of ASIL D safety. Wow, what a journey, right? We've just traced how modern EV inverters essentially survive a war against physics itself, from microscopic thermal modeling all the way to brutal real-world validation. And it leaves us with a pretty profound question to wrap up on. As electric vehicles get even faster and push even higher voltages in the years to come, are these nanosecond defenses going to be enough? Or will physics force us to invent entirely new ways to manage heat? Well, maybe diving into a Foster 4-stage RC thermal network dynamic simulation report is your next step to find out. Keep learning and stay curious.